So in the previous 2 weeks, we've talked about how to set up our models, our first level models, which is the time series analysis that we do that allows us to estimate the effects at that first level, and then also what I called second level or higher level modeling, that is the fixed effects and random effects models. This week, I want to talk about how we draw statistical inference based on those models that we've set up. And at some level, this is kind of the most exciting step, but it can also be somewhat intimidating because the math is hairy. I want to give you a feel for the math without sort of going into the equations in any depth. I'm going to, I think, mention one equation this week. But the key here is I'm going to try to give you a graphical presentation of the way we use statistical inference with fMRI data. And I'm going to do this in 3 videos. And the first video, I want to talk about the multiple comparison problem that we face in fMRI, what it is and how we can begin to start to address it. In the second video, I'm going to talk about Gaussian random field theory, which is the way we're going to approach solving this inference problem. How do we set statistical thresholds so that we can get meaningful activation? And then in the third and final video, I want to talk about some variants on that. So something called cluster thresholding and what it's good for and maybe some of its limitations a little bit. And also how we can deal with the multiple comparison problem if we have a restricted space. So if we're interested in some sort of region of interest analysis, how do we constrain the multiple comparison problem so that we're actually testing the hypothesis that we have rather than doing some sort of whole brain, more conservative testing. So this week's aims are to review the basics of significant testing. So I just want to make sure everybody's on the same page. And then I'm going to introduce the idea of a resolution element, right? So we've talked about pixels as picture elements in a 2-dimensional plane, like on a TV or on a computer screen. And then we've talked about voxels as 3-dimensional elements. A resol is also a 3-dimensional element that takes into account some of the practicalities of what we're doing, independent of the actual number of voxels. As I said in the second video, I'm going to introduce Gaussian random field theory and how we use it to generate inference. And then I'm going to talk at some length about voxel-wise versus cluster-wise statistical thresholding and the strengths and weaknesses of both approaches. So I'd like to begin by reviewing sort of the basics of inference and then getting into this multiple comparison problem. The simplest type of statistic that we can do are basically descriptive statistics. So that is to say, to measure effect sizes, to measure variance and things like that. We're not drawing any conclusions from these. These are just simple ways of summarizing the data so that we have a feel for a much more complex data set into a simpler kind of constraint. So, for instance, the effect size, the percent bold signal change, is a descriptive statistic. It doesn't tell us whether it's a meaningful change. All it tells us is the size of the bold signal change. Similarly, the amount of variability across the brain is a summary statistic, a descriptive statistic, because it tells you how variable each of those areas are, independent of whether or not that variation is meaningful. So on the right here, what I have is a colorized plot of effect sizes of a particular study. Hopefully you can see just from the heat maps here that this is something that definitely seems to involve visual presentation, because visual cortex is showing the greatest effect sizes with those yellow-red colors, whereas the rest of the brain, at least at the more ventral levels, is sort of these cool blue-greens. As you get higher, you also can see that there seems to be some sort of motor cortex activity. So I imagine it's some sort of visual paradigm that engages motor cortex. For instance, the visual stimulation that allows you to then do your finger tapping task that I keep returning to time and time again. Okay. Those summary statistics are useful, but they don't allow you to make any sort of inference. They don't allow you to say, well, what does it mean? Is it a significant change, or is it just a change that we would have seen by chance? And it doesn't allow you to quantify how confident you are in whatever your interpretation is. So that's when we're moving from description to inference, when we want to start to say, is this meaningful? And if so, how confident in that meaning can I be? So one thing that you might ask in a very simple way is there any sort of difference between the activation in the left and right hemispheres? Maybe this is a task that you expected to activate one particular hemisphere more than the other, in which case you'd like to be able to quantify that. And when you get to that level of question, then you have a hypothesis. You have an implicit hypothesis in this case, which is that the one hemisphere is more active than the other hemisphere. And the null hypothesis in this case would be simply, no, there's no difference between the two hemispheres. But once we have those hypotheses in place, we can do hypothesis testing, and that is do statistical inference. So to just make this really concrete, I'm going to hypothesize that activation in the right hemisphere is larger than activation in the left hemisphere. And in this case, by activation, I simply mean the effect sizes induced by the task of interest. And I have all those values, so I can compute the mean over the right and the left hemispheres and say, well, the mean effect size is almost 0.4% bold in the right, and it's closer to 0.1% in the left hemisphere. So numerically, there's a difference, and that difference clearly fits my hypothesis. The next question then is that meaningful, or is that something that we would expect just by chance? So just looking at the mean effects doesn't really tell you that. We also need to consider the variation there. And in this case, I'm going to assume that the variance in both hemispheres is the same because, I'm not assuming that. I've actually calculated it from the data. But in this case, they end up being the same. And with those two figures, we can start to test our hypothesis a little bit more rigorously. And what we can say is this difference between the right and the left hemisphere significant? Is it something that's meaningful that you would expect to occur if it wasn't just by chance? So the odds that this occur by chance are very low. And specifically, we normally assume very low to mean there's a 1 in 20 chance or a 0.05 chance that it's happened just randomly. And the way we do this is just using a t-test. And again, I'm sure that you've seen this loads and loads of times, so I apologize for sort of rushing through this material, but I'm assuming that it's basically familiar to people. If it's not, hopefully I'm going to give you a little bit of a foundation for it, and you may then want to go back to sort of an intro stats class where you can look at what is a t-test and how you can be used in significance testing. So the only equation that I'm going to share today, again, is that t equation. I did it last week. In this case, I'm going to make it even simpler. The t statistic is the ratio of the effect size to the noise. That's all it is, right? So we've calculated the effects. We've calculated the noise in the previous example. So we can say, well, the effect size is how big a difference is there between, for instance, finger tapping and rest. And that was the mean that I showed you 2 slides ago. And then the noise is how confident you are. How noisy are these data? The larger the noise value, the less confident you are. And that's just the variance across the left hemisphere and the right hemisphere. What this means is as the t value goes large, then the effect is more significant. You can be more confident in it, right? So if the ratio of the effect size to the noise, the signal to the noise, is greater, of course you're more confident in it. And there's multiple ways that this can happen, right? I mean, it could be the case that you have a really large effect size and then you just have some sort of midland noise level. So the larger the effect size relative to the noise, of course, that would lead to a larger t. On the other hand, the contrary version of that is a big effect size by itself isn't necessarily meaningful if you also have a lot of noise, right? Because then the ratio of the big effect to the big noise is a relatively small t. It also means that you can have small effect sizes that are highly significant as long as the noise is very small. So that is to say, you don't need massive effect sizes. I mean, if you remember, the value was 0.37% bold signal change. In the scheme of things, that just does not sound like a big effect. But if the variance is sufficiently small, it could still be significant because the ratio of the signal, the effect, to the noise is high. So let's look at this sort of empirically. These are histograms of the effect sizes across the hemisphere. And you could see, if you recall from the image, that there were bright spots that were the sort of red-yellow, there were cooler spots that were blue-green. That means that there are differences in effect sizes across the voxels in the left hemisphere and in the right. And what I've done is I've just sort of plotted them in a sort of histogram here. And when I look at them, they have two different means. Those are the values that we saw before. The mean in the left is only 0.05. The mean in the right is 0.37. So the means are different, but the variance of the curves was the same. They were both 0.16%, right? So that is to say that the curves' shapes are essentially identical. The only thing that's different are the means that are shifted left-right here in this case. And once we have that, we can just use those summary statistics, those curves without the histograms underneath them, to say, well, is the difference between these two curves significant? And the answer is, it depends on how you set your threshold. So if you set your threshold very high, if you say, well, I only am interested if they're different, if it could only happen one time in 100, so a p-value of 0.01, then you can see that actually the peaks of both curves are to the left of that threshold value. That suggests that there's nothing to separate them at that level. So there's no significant difference between them. On the other hand, if you set the threshold very low, say you're going to accept 4 times out of 10, this could happen by chance, 0.40 p-value, then clearly you can see that there's a difference because the peaks are on either side of that threshold line. On the other hand, like 40% of the curve is, the left-hand curve is on that side too, which means that the chance of a false positive, the fact that you would accept that, yes, these are different when in fact they really aren't and that it occurred by chance, is very, very high. So that's a risk, and the answer, typically, is that we use a p-value of 0.05. There is nothing magical about 0.05, right? It is a convention that's accepted very, very widely in science. It's used across disciplines, but it is a convention. So you have to realize that it's an arbitrary decision that sort of we've decided on as a group, as a community, and we're more or less happy with it as a community. There are certainly issues, and we could certainly talk about them. But what that means is, in this particular case, the peaks of the left and the right are separated. So yes, there is a significant difference between them. But of course, there's still a part of that green curve, the left-hand curve, that is to the right of that threshold, which means that there is, in this case, a 5% or 1 in 20 chance of accepting that there's a real difference when there isn't, when it just occurred by chance. But that's the convention that we as a community have accepted. It's worth pointing out that not all aspects of science use 0.05. There are areas where people use more stringent criteria. So for instance, if you're looking for a new particle in physics, so the people at CERN who were looking for the Higgs boson, for instance, to identify a new fundamental particle in physics, the physics community has accepted we're not going to use a 1 in 20 chance of a false positive because that's a ridiculously lenient thing for such a fundamental kind of contribution. In that case, they use what's called a 5 sigma level of significance, or in our terms today, that means a z-score of 5 or greater. And I don't really want to talk about the relationship between z-scores and sigma and things because again, I hope you've seen it before. If you haven't, it's certainly worth looking up the relationship between how z-scores come about. But if it's something fundamental that shifts the way we're going to think about science, we're going to use a much, much more stringent threshold in general. Okay. However, that's only appropriate if you're only effectively doing a single test. The question is, what if you have more than... Oh, sorry, I'm getting ahead of myself. What I'm going to say here is, what if you only have a single distribution? What if you only want to test activation in one condition? Well, in that case, what we do is we assume a normal distribution as the null. So I'm not comparing left to right. I just want to say, is there significant activation in the left hemisphere or in the right hemisphere, whichever the case may be, but not relative to the other. So in that case, I only have the one distribution. So I'm going to compare it to a normal distribution. That is a distribution that's centered on 0 and that has a standard deviation or a variance of 1. Right? So we've got a mean of 0, we've got a standard deviation here of 1, and that becomes the second curve that we compare them to. This is the default hypothesis, the null hypothesis. And all we do is we test our data, the measurements that we've taken, against this assumed standard normal distribution. So this is what's called a one-sample t-test because you only have data from one group and you're comparing it to an assumed normal distribution. And obviously the difference depends on the significance depends on the difference in the means. So that is the effect size. Whatever the mean that you measured, how different is that from zero? And then it also depends on the noise, the variance of those curves. How wide is the empirical data that you measured? The wider it is, the greater the noise, the less likelihood that you're going to find a significant difference because that t statistic means that you're dividing it by a larger number in the denominator. The noise is larger. So if you have a wider curve here, despite the fact the effect size is the same, you're less likely to have a significant effect. Thresholding for a single test is easy. We're going to just stick with 0.05. P is less than 0.05. What happens, though, if you have like 20 tests? So we have 20 different things that we've measured. And if we threshold all of them at 0.05, then we run a significant risk of false positive. That is to say, accepting something as a significant difference that actually happened by chance. So in this particular plot, what I've done is I've shown 20 normal normal distributions. And what I've done is I've chosen a random number from those 20 distributions just using MATLAB. So they are completely random. There is no signal in this. It's noise. But what you can see is that by chance, one of these distribution actually exceeds that 0.05 threshold. And you can see it's in the second row and on the left with an asterisk. So this is about what you would expect, right? If you have 20 tests and you have a 1 in 20 chance of a false positive, then on average you would expect that about one of those tests is going to be positive just by chance. What that means for us is that as soon as we have more than one test, it inflates our rate of false positives from 1 in 20, which is our community standard, to something higher than that, which becomes risky and in most cases unacceptable. Now, the problem is that with how do we deal with this, right? So the most commonly accepted method is a correction that was proposed by Carlo Emilio Bonferroni, shown here on the right. And the idea here is simply that what we need to deal with is the family-wise error. So not the test-wise error. Each test is going to have a particular error threshold. How do we set that test threshold such that across the whole set of tests that we're going to do, the family of tests, we have a 0.05 threshold of what makes something significant. So if you have one test, then the whole family is 1 and the p value is 0.05 and life is easy. If you have 2 tests, however, then you've got the family-wise error is greater than 0.05. So how do we correct for that? Well, what Bonferroni said was, we'll just divide the family-wise error that you're interested in, which in our case is going to be 0.05, by the number of tests. So if you have 2 tests, you divide 0.05 by 2, and you get 0.025, right? Or if you have 10 tests, then you divide 0.05 by 10, and you get 0.005. So it's a very simple, very straightforward way of correcting for the multiple comparisons problem. How many comparisons do you have? Divide 0.05 by that. And that's the threshold that you use for each of the individual tests. Right, and this is what I've just said. If you, in the case that I presented before with 20 random tests, then you would divide 0.05 by 20, and you'd find out that the p-value that you need is 0.0025. And in fact, if you apply that to the random numbers that I had on that example, none of them are significant, which is exactly what you'd want, given that I generated them randomly. They are noise. The issue comes from the fact that if you look at the number of voxels in the brain, you could easily have 250,000 in there, particularly if you're looking at a structural scan where you did 1 by 1 by 1 millimeter scan and you're doing some sort of voxel-based morphometry or something along those lines. What happens then? I mean, if you're going to do a mass univariate approach, then you are literally applying statistical threshold to each and every voxel in the brain. If that's a structural scan or a set of structural scans you're looking at, then it could be 250,000 examples. If it's a functional scan, it's still going to be on the order of probably 25 to 30,000 tests? Do we want to divide 0.05 by these kind of numbers, right? So for instance, if you took 0.05 and said, well, I've got 250,000 tests, then the p-value that you would need at each voxel to pass this threshold would be 0.000000197, right? It's a very, very small number. And just because it becomes really inconvenient to start looking at however many zeros and then these really small numbers, we tend to convert these p-values to z-scores instead. So for instance, the p-value on your screen actually corresponds to a z-score of 5.07. So if you had a z-score of 5.7 or larger, then you would consider it significant. I mentioned already that there's a relationship between p-scores and z-scores. And the gist is that a z-score is how many standard deviations away from the mean do I need to be? And one standard deviation corresponds to z of 1. So in this case, this p-value would correspond to being 5 standard deviations away from the mean, which again is that 5 sigma level that I was talking about with, for instance, particle physics. So we're going to deal with some very similar thresholds in terms of fMRI because of the number of statistical comparisons that we're doing. So we're not doing it because we want to be unreasonably confident that this is a real thing. We're doing this to accept our confidence value of there's a 1 in 20 chance that this activation is legitimate. It's just that we have so many data points that we're testing in parallel that we need to take the multiple comparison problem very seriously.